Yellow fever.
Yellow fever, known historically as yellow jack, or yellow plague, is an acute viral disease. In most cases symptoms include fever, chills, loss of appetite, nausea, muscle pains particularly in the back, and headaches. Symptoms typically get better within 5 days. In some people within a day of improving the fever comes back, there is abdominal pain, and liver damage begins causing yellow skin. If this occurs, there is also an increased risk of bleeding and kidney problems. The disease is caused by the yellow fever virus and is spread by the bite of the female mosquito. It only infects humans, other primates and several species of mosquito. In cities it is primarily spread by mosquitoes of the Aedes aegypti species. The virus is an RNA virus of the genus Flavivirus. The disease may be difficult to tell apart from other illnesses, especially in the early stages. To confirm a suspected case, blood sample testing with PCR is required. A safe and effective vaccine against yellow fever exists, and some countries require vaccinations for travelers. Other efforts to prevent infection include reducing the population of the transmitting mosquito. In areas where yellow fever is common and vaccination is uncommon, early diagnosis of cases and immunization of large parts of the population is important to prevent outbreaks. Once infected, management is symptomatic, with no specific measures effective against the virus. In those with severe disease, death occurs in about half of people without treatment. Yellow fever causes 200,000 infections and 30,000 deaths every year, with nearly 90% of these occurring in Africa. Nearly 1 billion people live in an area of the world where the disease is common. It is common in tropical areas of South America and Africa, but not in Asia. Since the 1980s, the number of cases of yellow fever has been increasing. This is believed to be due to fewer people being immune, more people living in cities, people moving frequently, and changing climate. The origin of the disease is Africa, from where it spread to South America through the slave trade in the 17th century. Since the 17th century, several major outbreaks of the disease have occurred in the Americas, Africa, and Europe. In the 18th and 19th century, yellow fever was seen as one of the most dangerous infectious diseases. The yellow fever virus was the first human virus discovered.
Signs and symptoms.
Yellow fever begins after an incubation period of 3 to 6 days. Most cases only cause a mild infection with fever, headache, chills, back pain, loss of appetite, nausea, and vomiting. In these cases the infection lasts only 3 to 4 days. In 15% of cases, however, sufferers enter a second, toxic phase of the disease with recurring fever, this time accompanied by jaundice due to liver damage, as well as abdominal pain. Bleeding in the mouth, the eyes, and the gastrointestinal tract will cause vomit containing blood, hence the Spanish name for yellow fever, vomito negro, black vomit. The toxic phase is fatal in approximately 20% of cases, making the overall fatality rate for the disease 3%, 15%, 20%. In severe epidemics, the mortality may exceed 50%. Surviving the infection provides lifelong immunity, and normally there is no permanent organ damage.
Cause.
Yellow fever is caused by the yellow fever virus, a 40 to 50 nanometers wide enveloped RNA virus, the type, species and namesake of the family Flaviviridae. It was the first illness shown to be transmissible via filtered human serum and transmitted by mosquitoes, by Walter Reed around 1900. The positive sense single-stranded RNA is approximately 11,000 nucleotides long and has a single open reading frame encoding a polyprotein. Host proteases cut this polyprotein into 3 structural, C, PRM, E, and 7 non-structural proteins, NS1, NS2A, NS2B, NS3, NS4A, NS4B, NS5. The enumeration corresponds to the arrangement of the protein-coding genes in the genome. Yellow fever belongs to the group of hemorrhagic fevers. The viruses infect, amongst others, monocytes, macrophages and dendritic cells. They attach to the cell surface via specific receptors and are taken up by an endosomal vesicle. Inside the endosome, the decreased pH induces the fusion of the endosomal membrane with the virus envelope. The capsid enters the cytosol, decays, and releases the genome. Receptor binding as well as membrane fusion are catalyzed by the protein E, which changes its conformation at low pH, causing a rearrangement of the 90 homodimers to 60 homotrimers. After entering the host cell, the viral genome is replicated in the rough endoplasmic reticulum, ER, and in the so-called vesicle packets. At first, an immature form of the virus particle is produced inside the ER, whose M protein is not yet cleaved to its mature form and is therefore denoted as PRM, precursor M, and forms a complex with protein E. The immature particles are processed in the Golgi apparatus by the host protein furin, which cleaves PRM to M. This releases E from the complex, which can now take its place in the mature, infectious virion.
Transmission.
Yellow fever virus is mainly transmitted through the bite of the yellow fever mosquito Aedes aegypti, but other mosquitoes such as the tiger mosquito, Aedes albopictus, can also serve as a vector for this virus. Like other arboviruses which are transmitted via mosquitoes, the yellow fever virus is taken up by a female mosquito when it ingests the blood of an infected human or other primate. Viruses reach the stomach of the mosquito, and if the virus concentration is high enough, the virions can infect epithelial cells and replicate there. From there they reach the haemocoel, the blood system of mosquitoes, and from there the salivary glands. When the mosquito next sucks blood, it injects its saliva into the wound, and the virus reaches the bloodstream of the bitten person. There are also indications for transvarial and transstadial transmission of the yellow fever virus within A. aegypti, that is, the transmission from a female mosquito to her eggs and then larvae. This infection of vectors without a previous blood meal seems to play a role in single, sudden breakouts of the disease. There are 3 epidemiologically different infectious cycles, in which the virus is transmitted from mosquitoes to humans or other primates. In the urban cycle, only the yellow fever mosquito Aedes aegypti is involved. It is well adapted to urban centers and can also transmit other diseases, including dengue fever and chikungunya. The urban cycle is responsible for the major outbreaks of yellow fever that occur in Africa. Except in an outbreak in 1999 in Bolivia, this urban cycle no longer exists in South America. Besides the urban cycle there is, both in Africa and South America, a sylvatic cycle, forest cycle or jungle cycle, where Aedes africanus, in Africa, or mosquitoes of the genus Haemogogus and Sabeths, in South America, serve as vectors. In the jungle, the mosquitoes infect mainly non-human primates. The disease is mostly asymptomatic in African primates. In South America, the sylvatic cycle is currently the only way humans can infect each other, which explains the low incidence of yellow fever cases on the continent. People who become infected in the jungle can carry the virus to urban centers, where Aedes aegypti acts as a vector. It is because of this sylvatic cycle that yellow fever cannot be eradicated. In Africa there is a third infectious cycle, also known as savanna cycle, or intermediate cycle, which occurs between the jungle and urban cycle. Different mosquitoes of the genus Aedes are involved. In recent years, this has been the most common form of transmission of yellow fever in Africa.
Pathogenesis.
After transmission of the virus from a mosquito, the viruses replicate in the lymph nodes and infect dendritic cells in particular. From there they reach the liver and infect hepatocytes, probably indirectly via Kupffer cells, which leads to eosinophilic degradation of these cells and to the release of cytokines. Necrotic masses known as Councilman bodies appear in the cytoplasm of hepatocytes. Fatality may occur when cytokine storm, shock, and multiple organ failure follow.
Diagnosis.
Yellow fever is a clinical diagnosis, which often relies on the whereabouts of the diseased person during the incubation time. Mild courses of the disease can only be confirmed virologically. since mild courses of yellow fever can also contribute significantly to regional outbreaks. Every suspected case of yellow fever, involving symptoms of fever, pain, nausea and vomiting 6 to 10 days after leaving the affected area, has to be treated seriously. If yellow fever is suspected, the virus cannot be confirmed until 6 to 10 days after the illness. A direct confirmation can be obtained by reverse transcription polymerase chain reaction where the genome of the virus is amplified. Another direct approach is the isolation of the virus and its growth in cell culture using blood plasma. This can take 1 to 4 weeks. Serologically, an enzyme-linked immunosorbent assay during the acute phase of the disease using specific IgM against yellow fever or an increase in specific IgG titer, compared to an earlier sample, can confirm yellow fever. Together with clinical symptoms, the detection of IgM or a fourfold increase in IgG titer is considered sufficient indication for yellow fever. Since these tests can cross-react with other flaviviruses, like dengue virus, these indirect methods can never prove yellow fever infection. Liver biopsy can verify inflammation and necrosis of hepatocytes and detect viral antigens. Because of the bleeding tendency of yellow fever patients, a biopsy is only advisable post-mortem to confirm the cause of death. In a differential diagnosis, infections with yellow fever have to be distinguished from other feverish illnesses like malaria. Other viral hemorrhagic fevers, such as Ebola virus, Lassa virus, Marburg virus and Junin virus, have to be excluded as cause.
Prevention.
Personal prevention of yellow fever includes vaccination as well as avoidance of mosquito bites in areas where yellow fever is endemic. Institutional measures for prevention of yellow fever include vaccination programs and measures of controlling mosquitoes. Programs for distribution of mosquito nets for use in homes are providing reductions in cases of both malaria and yellow fever.
Vaccination.
Vaccination is recommended for those traveling to affected areas, because non-native people tend to suffer more severe illness when infected. Protection begins by the 10th day after vaccine administration in 95% of people, and lasts for at least 10 years. About 81% of people are still immune after 30 years. The attenuated live vaccine Stem 17D was developed in 1937 by Max Theiler. The WHO recommends routine vaccinations for people living in affected areas between the 9th and 12th month after birth. Up to 1 in 4 people experience fever, aches, and local soreness and redness at the site of injection. In rare cases, less than 1 in 200,000 to 300,000, the vaccination can cause yellow fever vaccine-associated viscerotropic disease, YELAVD, which is fatal in 60% of cases. It is probably due to the genetic morphology of the immune system. Another possible side effect is an infection of the nervous system, which occurs in 1 in 200,000 to 300,000 cases, causing yellow fever vaccine-associated neurotropic disease, YELAND, which can lead to meningoencephalitis and is fatal in less than 5% of cases. In 2009, the largest mass vaccination against yellow fever began in West Africa, specifically Benin, Liberia, and Sierra Leone. When it is completed in 2015, more than 12 million people will have been vaccinated against the disease. According to the World Health Organization, WHO, the mass vaccination cannot eliminate yellow fever because of the vast number of infected mosquitoes in urban areas of the target countries, but it will significantly reduce the number of people infected. The WHO plans to continue the vaccination campaign in another 5 African countries, Central African Republic, Ghana, Guinea, Côte d'Ivoire, and Nigeria, and stated that approximately 160 million people in the continent could be at risk unless the organization acquires additional funding to support widespread vaccinations. In 2013, the World Health Organization stated a single dose of vaccination is sufficient to confer lifelong immunity against yellow fever disease.
Compulsory vaccination.
Some countries in Asia are theoretically in danger of yellow fever epidemics, Mosquitoes with the capability to transmit yellow fever and susceptible monkeys are present, although the disease does not yet occur there. To prevent introduction of the virus, some countries demand previous vaccination of foreign visitors if they have passed through yellow fever areas. Vaccination has to be proven in a vaccination certificate which is valid 10 days after the vaccination and lasts for 10 years. A list of the countries that require yellow fever vaccination is published by the WHO. If the vaccination cannot be conducted for some reasons, dispensation may be possible. In this case, an exemption certificate issued by a WHO-approved vaccination center is required. Although 32 of 44 countries where yellow fever occurs endemically do have vaccination programs, in many of these countries, less than 50% of their population is vaccinated.
Vector control.
Control of the yellow fever mosquito Aedes aegypti is of major importance, especially because the same mosquito can also transmit dengue fever and chikungunya disease. Aedes aegypti breeds preferentially in water, for example in installations by inhabitants of areas with precarious drinking water supply, or in domestic waste, especially tires, cans and plastic bottles. These conditions are common in urban areas in developing countries. Two main strategies are employed to reduce mosquito populations. One approach is to kill the developing larvae. Measures are taken to reduce the water accumulations in which the larva develops. Larvicides are used, as well as larva-eating fish and copepods, which reduce the number of larvae. For many years, copepods of the genus Mesocyclops have been used in Vietnam for preventing dengue fever. It eradicated the mosquito vector in several areas. Similar efforts may be effective against yellow fever. Pyriproxyfen is recommended as a chemical larvicide, mainly because it is safe for humans and effective even in small doses. The second strategy is to reduce populations of the adult yellow fever mosquito. Lethal V-traps can reduce Aedes populations, but with a decreased amount of pesticide because it targets the mosquitoes directly. Curtains and lids of water tanks can be sprayed with insecticides, but application inside houses is not recommended by the WHO. Insecticide-treated mosquito nets are effective, just as they are against the Anopheles mosquito that carries malaria.
Treatment.
As for other flavivirus infections, there is no cure for yellow fever. Hospitalization is advisable and intensive care may be necessary because of rapid deterioration in some cases. Different methods for acute treatment of the disease have been shown to not be very successful. Passive immunization after emergence of symptoms is probably without effect. Ribavirin and other antiviral drugs as well as treatment with interferons do not have a positive effect in patients. Asymptomatic treatment includes rehydration and pain relief with drugs like paracetamol, known as acetaminophen in the United States. Acetylsalicylic acid, aspirin, should not be given because of its anticoagulant effect, which can be devastating in the case of inner bleeding that can occur with yellow fever.
Epidemiology.
Yellow fever is endemic in tropical and subtropical areas of South America and Africa. Even though the main vector Aedes aegypti also occurs in Asia, in the Pacific, and in the Middle East, yellow fever does not occur in these areas. The reason for this is unknown. Worldwide there are about 600 million people living in endemic areas. WHO officially estimates that there are 200,000 cases of disease and 30,000 deaths a year. The number of officially reported cases is far lower. An estimated 90% of the infections occur on the African continent. In 2008, the largest number of recorded cases were in Togo. Phylogenetic analysis identified 7 genotypes of yellow fever viruses, and it is assumed that they are differently adapted to humans and to the vector Aedes aegypti. 5 genotypes, Angola, Central East Africa, West Africa I, and West Africa II, occur only in Africa. West Africa genotype I is found in Nigeria and the surrounding areas. This appears to be especially virulent or infectious as this type is often associated with major outbreaks. The three genotypes in East and Central Africa occur in areas where outbreaks are rare. Two recent outbreaks in Kenya, 1992 to 1993, and Sudan, 2003 and 2005, involved the East African genotype, which had remained unknown until these outbreaks occurred. In South America, two genotypes have been identified, South American genotype I and II. Based on phylogenetic analysis, these two genotypes appear to have originated in West Africa and were first introduced into Brazil. The date of introduction into South America appears to be 1822, 95% confidence interval 1701 to 1911. The historical record showed that there was an outbreak of yellow fever in Recife, Brazil, between 1685 and 1690. The disease seems to have disappeared, with the next outbreak occurring in 1849. It seems likely that it was introduced with the importation of slaves through the slave trade from Africa. Genotype I has been divided into 5 subclades, A through E.
History.
The evolutionary origins of yellow fever most likely lie in Africa, with transmission of the disease from primates to human beings. It is thought that the virus originated in East or Central Africa and spread from there to West Africa. As it was endemic in Africa, the natives had developed some immunity to it. When an outbreak of yellow fever would occur in an African village where colonists resided, most Europeans died, while the native population usually suffered non-lethal symptoms resembling influenza. This phenomenon, in which certain populations develop immunity to yellow fever due to prolonged exposure in their childhood, is known as acquired immunity. The virus, as well as the vector A. aegypti, were probably transferred to North and South America with the importation of slaves from Africa, part of the Columbian exchange following European exploration and colonization. The first definitive outbreak of yellow fever in the New World was in 1647 on the island of Barbados. An outbreak was recorded by Spanish colonists in 1648 in Yucatan, Mexico, where the indigenous Mayan people called the illness xechic, blood vomit. In 1685, Brazil suffered its first epidemic, in Recife. The first mention of the disease by the name yellow fever occurred in 1744. Although yellow fever is most prevalent in tropical-like climates, the northern United States was not exempted from the fever. The first outbreak in English-speaking North America occurred in New York in 1668, and a serious one afflicted Philadelphia in 1793. English colonists in Philadelphia and the French in the Mississippi River Valley recorded major outbreaks in 1669, as well as those occurring later in the 18th and 19th centuries. The southern city of New Orleans was plagued with major epidemics during the 19th century, most notably in 1833 and 1853. At least 25 major outbreaks took place in the Americas during the 18th and 19th centuries, including particularly serious ones in Cartagena in 1741, Cuba in 1762 and 1900, Santo Domingo in 1803, and Memphis in 1878. Major outbreaks have also occurred in southern Europe. Gibraltar lost many to an outbreak in 1804, in 1814, and again in 1828. Barcelona suffered the loss of several thousand citizens during an outbreak in 1821. Urban epidemics continued in the United States until 1905, with the last outbreak affecting New Orleans. Due to yellow fever, in colonial times and during the Napoleonic Wars, the West Indies were known as a particularly dangerous posting for soldiers. Both English and French forces posted there were decimated by the Yellow Jack. Wanting to regain control of the lucrative sugar trade in Saint-Domingue, and with an eye on regaining France's New World Empire, Napoleon sent an army under the command of his brother-in-law to Saint-Domingue to seize control after a slave revolt. The historian J. R. McNeill asserts that yellow fever accounted for approximately 35,000 to 45,000 casualties of these forces during the fighting. Only one-third of the French troops survived for withdrawal and returned to France. Napoleon gave up on the island, and in 1804 Haiti proclaimed its independence as the Second Republic in the Western Hemisphere. The yellow fever epidemic of 1793 in Philadelphia, which was then the capital of the United States, resulted in the deaths of several thousand people, more than 9% of the population. The national government fled the city, including President George Washington. Additional yellow fever epidemics struck Philadelphia, Baltimore and New York in the 18th and 19th centuries, and traveled along steamboat routes from New Orleans. They caused some 100,000 to 150,000 deaths in total. In 1858, St. Matthew's German Evangelical Lutheran Church in Charleston, South Carolina, suffered 308 yellow fever deaths, reducing the congregation by half. In 1873, Shreveport, Louisiana lost almost a quarter of its population to yellow fever. In 1878, about 20,000 people died in a widespread epidemic in the Mississippi River Valley. That year, Memphis had an unusually large amount of rain, which led to an increase in the mosquito population. The result was a huge epidemic of yellow fever. The steamship John D. Porter took people fleeing Memphis northward in hopes of escaping the disease, but passengers were not allowed to disembark due to concerns of spreading yellow fever. The ship roamed the Mississippi River for the next 2 months before unloading her passengers. The last major U.S. outbreak was in 1905 in New Orleans. Ezekiel Stone Wiggins, known as the Ottawa Prophet, proposed that the cause of a yellow fever epidemic in Jacksonville, Florida, in 1888 was astronomical. Carlos Finley, a Cuban doctor and scientist, first proposed in 1881 that yellow fever might be transmitted by mosquitoes rather than direct human contact. Since the losses from yellow fever in the Spanish-American War in the 1890s were extremely high, Army doctors began research experiments with a team led by Walter Reed, composed of doctors James Carroll, Aristides Agramonte and Jesse William Lazer. They successfully proved Finley's mosquito hypothesis. Yellow fever was the first virus shown to be transmitted by mosquitoes. The physician William Gorgas applied these insights and eradicated yellow fever from Havana. He also campaigned against yellow fever during the construction of the Panama Canal, after a previous effort on the part of the French failed, in part due to mortality from the high incidence of yellow fever and malaria, which decimated the workers. Although Dr. Reed has received much of the credit in United States history books for beating yellow fever, he had fully credited Dr. Finley with the discovery of the yellow fever vector, and how it might be controlled. Dr. Reed often cited Finley's papers in his own articles, and also gave him credit for the discovery in his personal correspondence. The acceptance of Finley's work was one of the most important and far-reaching effects of the Walter Reed Commission of 1900. Applying methods first suggested by Finley, the United States government and Army eradicated yellow fever in Cuba and later in Panama, allowing completion of the Panama Canal. While Dr. Reed built on the research of Carlos Finley, historian François Delaporte notes that yellow fever research was a contentious issue. Scientists, including Finley and Reed, became successful by building on the work of less prominent scientists, without always giving them the credit they were due. Dr. Reed's research was essential in the fight against yellow fever. He should also receive full credit for his use of the first type of medical consent form during his experiments in Cuba, an attempt to ensure that participants knew they were taking a risk by being part of testing. During 1920 to 1923, the Rockefeller Foundation's International Health Board, IHB, undertook an expensive and successful yellow fever eradication campaign in Mexico. The IHB gained the respect of Mexico's federal government because of the success. The eradication of yellow fever strengthened the relationship between the U.S. and Mexico, which had not been very good in the past. The eradication of yellow fever was also a major step toward better global health. In 1927, scientists isolated the yellow fever virus in West Africa. Following this, 2 vaccines were developed in the 1930s. The vaccine 17D was developed by the South African microbiologist Max Theiler at the Rockefeller Institute in New York City. This vaccine was widely used by the U.S. Army during World War II. Following the work of Ernest Goodpasture, Theiler used chicken eggs to culture the virus and won a Nobel Prize in 1951 for this achievement. A French team developed the French neurotropic vaccine, FNV, which was extracted from mouse brain tissue. Since this vaccine was associated with a higher incidence of encephalitis, FNV was not recommended after 1961. 17D is still in use and more than 400 million doses have been distributed. Little research has been done to develop new vaccines. Some researchers worry that the 60-year-old technology for vaccine production may be too slow to stop a major new yellow fever epidemic. Newer vaccines, based on vero cells, are in development and should replace 17D at some point. Using vector control and strict vaccination programs, the urban cycle of yellow fever was nearly eradicated from South America. Since 1943 only a single urban outbreak in Santa Cruz de la Sierra, Bolivia, has occurred. But, since the 1980s, the number of yellow fever cases have been increasing again, and A. aegypti has returned to the urban centers of South America. This is partly due to limitations on available insecticides, as well as habitat dislocations caused by climate change. It is also because the vector control program was abandoned. Although no new urban cycle has yet been established, scientists believe that this could happen again at any point. An outbreak in Paraguay in 2008 was thought to be urban in nature, but this ultimately proved not to be the case. In Africa, virus eradication programs have mostly relied upon vaccination. These programs have largely been unsuccessful because they were unable to break the sylvatic cycle involving wild primates. With few countries establishing regular vaccination programs, measures to fight yellow fever have been neglected, making the future spread of the virus more likely.
Research.
In the hamster model of yellow fever, early administration of the antiviral ribavirin is an effective early treatment of many pathological features of the disease. Ribavirin treatment during the first 5 days after virus infection improved survival rates, reduced tissue damage in the liver and spleen, prevented hepatocellular steatosis, and normalized levels of alanine aminotransferase, a liver damage marker. The mechanism of action of ribavirin in reducing liver pathology and yellow fever virus infection may be similar to its activity in treatment of hepatitis C, a related virus. Because ribavirin had failed to improve survival in a virulent rhesus model of yellow fever infection, it had been previously discounted as a possible therapy. In the past, yellow fever has been researched by several countries as a potential biological weapon.